This assessment asks us to predict a mechanism for this decarboxylation reaction. Our goal in this mechanism is to remove carbon dioxide using these esters and Cl- as a nucleophile. So the first step of this mechanism is going to be Cl- attacking the carbon of the ester alkoxy group that builds up too much electron density around this carbon. So we break the carbon-oxygen bond. We use the electrons in that bond to form a carbon-oxygen double bond. That will be the second carbon-oxygen double bond of carbon dioxide. That's going to build up too much electron density around carbon 1, so we'll break the 1,2 bond, use that to form a double bond between 2 and 3, kicking electrons up onto oxygen. That will form a new intermediate, an enolate intermediate at carbon number 3. And this enolate can be neutralized with water. Take a lone pair of electrons from oxygen, use the electrons on carbon 2 to grab water and get protonated. And then we'll do the same thing with the ester on the other side. So we'll use Cl- to attack the carbon of the alkoxy group of the ester, build up too much electron density around carbon, so we break the carbon-oxygen bond, form the second double bond of carbon dioxide. That builds up too much electron density around the carbonyl carbon, so we break the bond to carbon number 6 and use that to form an enolate between carbon 6 and carbon 7. And then that enolate, again, can be protonated by water to complete this reaction. Let's bring our carbon numbers back, make sure we got everything in the right place. And that will lead us to our final products for this reaction. So this mechanism is how we can decarboxylate beta diketones or beta diesters and beta ketoesters using Cl- as a nucleophile.